Not that anyone's counting, but this is the 27th edition of the QA, part of the Guide to Space. So as always, you've got questions, just type them in on any video that you're watching. I'll scoop a bunch of them up and answer them here. All right, let's get started. Black Frag Films. Hi, what camera are you using? Looks phenomenal. So about 3 months ago, we switched from using a Canon 5D Mark II to a brand new Lumix GH5. And it's actually shooting in 4K right now. And actually I got that as part of being involved in the YouTube Next Up program. So they give all of the people at Next Up a certificate and they can go into a camera store and they can get an upgrade. And so we got this upgrade to our camera gear and it's phenomenal. But that's kind of only half the story. The other half is that we sort of have improved the lighting setup. So we didn't used to bring lights with us into the forest, but my lovely camera wife, Carla, decided that we really needed to improve the light. She's a photographer, so she kind of knows what she's doing. And so she brought in the lights, and so now there's like lights in front of me here in the forest. And so I'm going to hold up my camera and I will take a shot of what it looks like from my perspective, and you can kind of see what's going on here. Hold on. All right, so here's the view from me, and there's Carla, and there's the lights. So, and that's the Lumix. And so now I'm going to shamelessly promote Carla's channel on YouTube and her Instagram channel. So, and I'll show you an example of the kinds of stuff that she does with both of them. We'll edit something in here. So check it out. And we'll put a link to the description below. So you should go and subscribe to her channel as well. Fico. Would it be possible to use an asteroid as a spaceship? It depends on the asteroid. So there's three kinds of asteroids, three types, right? There are the ones that are like big rocks, and they would be okay. There's the ones that are metal, and they would be great. And then there's the ones that are just like piles of rubble, and they would not be good, right? Because they're held together by their mutual gravity, and they're really just a bunch of balls of rock. So what could you do, right? You would go and find some asteroid, you would drill into it, you would hollow out a chunk of it, as much as the asteroid could withstand, and then you could set it rotating. And then you would have gravity, artificial gravity, inside this asteroid that you could then live on. So actually, asteroids will make some of the best places for us to go before we can build our own gigantic space stations in the solar system. I mean, we should totally get on that. And then my co-host for Astronomy Cast, Dr. Pamela Gay, she loves the idea of turning one of these asteroids into a colony ship. So take an asteroid, hollow it out, get it spinning, and then put some big thrusters on it, and then take it to another star system. The problem is that a lot of these asteroids, they're a lot more fragile than I think we thought before. And so if we do set them spinning and hollow out a lot of them, they could crack and fall apart. So we need to be really careful about how we do it. But in theory, they're great places to start. TN Spinsy. Talking about stars that don't give out light. What would black dwarfs be like or look like, you know, when the universe reaches the heat death? All right, so the idea of a black dwarf, this is a white dwarf, which is like the remnant of a star like our sun, that has died and is just slowly cooling down to the background temperature of the universe. And it actually takes a long, long time. There are none of these yet, because it'll take trillions or quadrillions of years for these things to cool down to the background temperature. So right now, they are bright and they're hot. But then over time, they would get cooler and cooler, and eventually they'd be room temperature, and then eventually they would be cold. And they are made of carbon. In fact, people talk about these white dwarfs as like the biggest diamond in the universe. And so you could kind of imagine, you know, what would it look like after it had cooled down to the background temperature? One gigantic diamond that's cold, which is kind of amazing. I'm Deathblade. Do you think humanity will one day manage to colonize the whole galaxy? What you're really talking about is the Fermi paradox, which is that will an alien civilization, in this case us, eventually reach a level of technology that we would colonize the entire galaxy? And there's nothing in the laws of physics that prevent it, but the problem is that the distances between the stars are so vast, right? They are light years away, and under our current rocket systems, we're looking at tens of thousands of years to make that journey. Maybe we can come up with something faster, so it would only take thousands or hundreds of years, but still, you know, we human beings are made of meat and we're very soft and very fragile. And so most likely it's going to be our robots that do this exploration. And I think it's highly likely that we will have the technology to build self-replicating robots where you send a robotic spaceship at a significant portion of the speed of light, it arrives at another star system, manufactures copies of itself, they go to other star systems, and you get this colonization of the entire Milky Way. And it wouldn't take that long. Like, it might take, you know, the Milky Way is 130,000 light years across. Let's say you could go 10% of the speed of light. It would take you, say, a couple of million years, maybe 10 million years to completely colonize the entire galaxy with your robots. I don't think humans would do it. Like I said, I don't think we're ever going to leave the solar system, unfortunately. It's just too far and we're just too soft. But I think our robots will do it. And then, of course, that brings up the question, if we could do it, why haven't the aliens done it? Where are all the aliens and where are all the alien robots? And that just goes back to that great puzzle. James 1010, is there dark matter in my room right now, even a tiny amount? Probably. Now, there's still an argument about what dark matter is. We still don't know, right? Some physicists think that dark matter is a tiny particle that doesn't interact with regular matter in any way, shape, or form, but it does have gravity. And other physicists think that no, it's just the way that gravity works over large distances and we don't really understand it. But the evidence, the overwhelming evidence now is in this particle camp. And so we have examples of particles that are everywhere, but they're very hard to detect. And the greatest example of that is neutrinos. There are neutrinos streaming off of the sun right now, and a neutrino stands a pretty good chance of making it through an entire light year of lead, of solid lead. You could take a neutrino, fire it through solid lead, and it would probably make it most of the way through that lead. So dark matter could be the same kind of thing, which is that it's this particle that doesn't interact, but there's a lot of it. We know that there's, you know, it makes up the largest proportion of the mass that's in the universe, and so chances are it's everywhere, all around you, all over the place. But we just can't detect it, we can't interact with it. And so that's all we know right now. Once the actual particle has been discovered, then we'll know how much of them there are, where they tend to be, what kind of interactions they have. But right now, it's all still a big mystery. Paul Cope. Hey Fraser, thanks for taking the time to answer questions. My question: if dark matter makes up roughly 23% of the mass of the universe, why can't we find evidence of it in our solar system? The same for dark energy. Why can we not find evidence of dark energy in our solar system? All right, so I kind of answered the dark matter part, which is that right now it just seems like this particle just does not interact in any way, shape, or form with regular matter except by gravity. Now, in theory, we could detect it by the gravity, but in a small localized level, there just is so little of it in terms of like the amount of space that there is in the Milky Way that any particles, we're just not going to be able to detect them. And it's the same thing for dark energy. So dark energy is this expansive force that is pushing the universe outward above and beyond its normal expansion. It's accelerating the expansion. And what it seems like is that you've got this force appearing at an equal amount for every cubic meter of the universe. So wherever you've got a cubic meter of space, you've got this expansive force that's pushing out. And so, but the thing is that on the small local levels, that force is infinitesimal. It's too tiny. It even can't push apart, say, the Milky Way, right? The Milky Way's gravity holds it together more strongly than the dark energy does. It's only when you, in fact, it's not even going to stop Andromeda from crashing into the Milky Way in a few billion years. It's only when you get across to the largest distances that the expansive force of dark energy takes over and is preventing objects from coming together. So the reason we can't really detect it is that it's just, we're in too small of a place for us to be able to detect something that's that slight. But over the largest distances, like how fast is that galaxy cluster speeding away from us, that we can detect. Cole Piss Drunk Hero. How much faster than C would one have to go in order to escape the gravity of a supermassive black hole at the center of the Milky Way? Right, so the idea of a black hole, right, is that you get this object where the gravity on it is so strong that nothing, the escape velocity to get off this object has exceeded the speed of light, so that nothing, no rocket can escape it, and light, any light that gets emitted comes back down. Now you would think that you would then, okay, well then you could calculate, some point where you could be going faster than light and be able to escape from a black hole. But the problem is that a black hole twists up space-time and tangles it up so much that there is no speed. Once you're within the event horizon, there's no getting out of it. There is no path, no direction that you can take that gets you out of the black hole. Even if you're going faster than the speed of light, all the paths lead you back into the singularity to your doom. So unfortunately, there is just no speed limit that would get you out of any black hole, be it a stellar one or a supermassive black hole. Tariki Pitt. Hey Fraser, you mentioned that fusion can only happen in stars up to iron. How then do we get the heavier elements like uranium? Does the neutron star produce heavier elements? This is really cool. When you get a very massive star, right? A star that is 10 times, 20 times the mass of our own sun, right? It's very hot. In the core, it's building up that core of different elements. It's going fusing heavier and heavier elements as it runs out of fuel until it gets up to iron. And then what happens is, because iron doesn't produce any energy when it fuses, essentially the output of energy from the core of the star just stops dead. And it happens in like a fraction of a second, like it's just turns off. And then all of the outward layers of the star collapse inward. And they come in at like 70% of the speed of light. So again, the whole star just goes and just collapses inward. And it's in that moment when the star is collapsing inward, when the black hole is forming, that all of those heavier elements are getting formed. So you've got, these forces coming in at the speed of light that are crushing these protons together to form the much larger, gold and uranium and all this kind of stuff. Now that's half the story, right? So what you get is then you get the explosion, all this material gets thrown out into space. But you've got a bunch of heavier elements, and these heavier elements are then decaying with radioactive decay into lighter elements. So in order to get all of the elements, and there's sort of a different path for all the different elements, and physicists have worked out all of the different ways this comes together. But essentially, in the moment when the supernova forms, when the black hole gets formed, you get the heavier elements, and then over long periods of time, as those heaviest elements decay radioactively, you get all the in-between elements as well. And that's how we get all the stuff that's heavier than iron in the universe, which is amazing. Next gen gaming. How do you know what's going on a lot of light years away, because it takes time for light to reach us? So we see those stars how they were years ago. It's true that we're seeing these stars in the past, right? We're seeing Alpha Centauri 4 years ago. We're seeing the center of the Milky Way 20,000 years ago. But the reality is that that's not that long ago in the age of a star. So our sun already has been burning for 4.5 billion years, right? Billion. Like Andromeda is only 2.5 million light years away. So there are galaxies that we do see that are 4.5 billion light years away, but that's far. So the reality is that as all the stars that we can see with our own eyes, they're only up to a couple of thousand years old. We can see Andromeda with our own eyes, but it's like 2.5 million years old from our vision. So really, everything that we see out there, it's not this moment, but it's kind of in real time. There's some interesting ideas, right? One is like this idea of the pillars of creation, which are these cool structures in the Eagle Nebula. And astronomers think that supernova have detonated within that region and collapsed the pillars. And so what we see right now is an old view of what the pillars actually look like right now, if you could go and see them, because we're seeing them several thousand years into the past. And in the future, eventually we'll see those supernova go off and they will collapse those pillars and we won't see them anymore. So, but really, it's like that saying, don't worry about, when you put your wish on stars, don't worry, they're dead just like your dreams. That's not true, right? Those stars are still alive, like your dreams. Sean Strange. A few videos ago, you talked about mining the solar system for resources. If you completely mined the gas and ice giants, wouldn't the mass distribution affect the rest of the planets and objects in the system in a potentially negative way? No, it would be positive, actually. Right now, actually, Jupiter is a very dangerous influence on the solar system. Astronomers have calculated that Jupiter has a pretty good chance of kicking out still Mercury from the solar system. It could even, there's a slight chance, like in billions and billions and billions of years, it could kick out Earth. Like, it is still a potentially destructive influence gravitationally. Same with Saturn, same with Uranus, same with Neptune, same with everything. You remove one of these planets and you make things more stable. You make less gravitational interactions in the solar system. So let's get rid of them. I'm just kidding. No, seriously, let's get rid of them. Jerry Ruprecht. If I was irresponsibly piloting my spacecraft and crashed into a random planet in our galaxy, how would I be able to locate where I am in relation to the Earth? I love this question, and it feels like it should be like a science fiction movie or something, although it'd be pretty nerdy. Anyway, and this is just like off the top of my head, so I'd love to hear your ideas as well. If I crashed, right, the first thing is to figure out, am I even in the Milky Way? Like, imagine you go through some kind of wormhole and then you appear and you crash into a planet and you're like, where am I? So the first thing you do is, if you had a really powerful telescope, is you would scan the sky and you would try to plot out the positions of the galaxies, because that would tell you if you're in the Milky Way. Now let's say that you are in the Milky Way. Then you would probably be plotting out the positions of the stars in the sky. And we actually, with the Gaia mission from ESA, it's going to map out 1 billion stars, the positions and movements of 1 billion stars out of the Milky Way's 200 billion. So a pretty big percentage, or 100 billion, but anyway, about 1% of the stars in the Milky Way, it'll know the positions of them. So you'll have very accurate star maps of all these different stars. You'll know what type of star they are, their position, where they are in relation to each other. So you should be able to figure that out. Now, if you were on the other side of the Milky Way, of the other side of the halo, and played in a region that was invisible to Earth, you could look at the position of the globular clusters, which some are above and below the plane of the Milky Way, and you could probably piece out where you are. The last thing is pulsars. On the Voyager spacecraft, there is the record, and on the record, the golden record, there is a map of pulsar positions, because pulsars actually, they repeat in a very, very specific way. And so you could look for all these different pulsars in the sky and figure out where you are in comparison to all of those pulsars compared to where you were from Earth. In fact, NASA has been sort of working out ways that they could use these pulsars just for all spacecraft to automatically navigate and position themselves just by, they would locate all the pulsars, they would calculate all the timings, and they would know where they are oriented in the universe, which is just an amazing idea. So there's a lot of stuff that you could do. Assuming you had a good telescope and a good star map, you could figure out where you landed pretty much anywhere in the galaxy. Stavros Papadakis. Why hasn't NASA created a mission to the zone of avoidance and passed to see the Great Attractor yet? Is it dangerous? The zone of avoidance, isn't that a great term? The zone of avoidance is the region of the sky where the galactic, where the center of the galaxy is. And the reason why astronomers call it the zone of avoidance is that they need to avoid it with their telescopes because they can't see past it. It is clogged with gas and dust and stars and material at the center of the galaxy, and it is like a wall that they couldn't see through in the past. Now, the trick is that in more recent times, there's different wavelengths of light, like infrared, that let you peer right through that gas and dust. And so now the zone of avoidance has actually gotten much, much smaller, and because of these infrared observatories like Spitzer and things like that, they can actually see through the plane of the galaxy and see the structures that are on the other side. And this idea of the Great Attractor, some object on the other side of the Milky Way that we couldn't see, that was in the zone of avoidance, was gathering material with its gravity. And now we can see it. It's a big galaxy cluster that accounts for this mass, and things are sort of sliding towards it gravitationally. Now, it's 26,000 light years away to get to the center of the of the Milky Way. It would take you millions of years at our current spacecraft to get to any kind of position where you could see past this region. So it's just too far. All right, that's it. Thanks everyone for putting in your questions. As always, if you're watching any video on my channel and you got a question either on the current video or you've just like a random space question, just go ahead and type it in. I'll gather a bunch of them here and I will answer them on this channel. Or I'll just type in answers because I do that quite a bit, as you've probably all noticed. All right, we'll see you all next week. And some argue that dark matter is a particle, and some argue that